In this video, I want to tackle a classic problem of racing rolling objects. We're going to have a series of rolling objects, spheres, and cylinders, and we want to send them down inclines and see which one will win. So to set it up, we have some set of rolling objects. They each have a mass m and radius r. And so we start with some cylinders, and we first have, say, a cylindrical shell. Now, such a cylindrical shell then has a moment of inertia of mr squared, the mass times the radius squared, because all the mass is at the edge. But if we have sort of a solid cylinder, then the moment of inertia is 1/2 the mr squared. It's still linear in mass and quadratic in the radius of the object, but there's a factor of 1/2, where if I would include the factor of 1 up above. So now if we go to our spheres, we can have a spherical shell, and the spherical shell has a moment of inertia of 2/3 times the mass times the radius of the sphere squared. And then with a solid sphere, we have a moment of inertia of 2/5 times the mass times the radius squared. And so you can see what I've done there is that all of the moments of inertia of these objects have the same form. They have a moment of inertia which is equal to some number k times the mass of the object times the radius of the object squared, where k then is a number greater than 0 and less than or equal to 1. And this k then sort of represents the distribution of matter relative to the axis of rotation. So the larger the value of k, the further away, on average, the mass is from the axis of rotation. So what does this tell us? We want to now look at this problem in terms of this parameter k. Okay, so we have incline, and we have an object rolling down the incline until it comes to the bottom, and it could be any one of these rotational objects, and which one is going to win the race? Well, the one that's going to win the race is the one that has the largest velocity. The one that can attain the largest velocity is going to be going faster, and so it's going to be the one that wins. So instead of just trying to work in terms of position and time, let's work in terms of velocities to see, as they fall, which one can attain the higher velocity, because that one is going to be going faster, and the one going faster is going to win. Okay, so let's look at conservation of energy for this problem. So this is going to, each mass is going to start with a height h, and so it's going to have some potential energy, and that energy is going to be converted into translational and rotational by the time it gets to the end. And let's see how that works. So what we're going to do then is we're going to assume arbitrary object, which means it could be any one of them. We're going to assume that the moment of inertia is some parameter k, mr squared, where k can be any number. So we're going to solve this problem in general for any object with a moment of inertia of that form. Okay, but since we've solved this problem before for a particular object, this shouldn't be so hard. It follows the same procedure. We have some initial energy, which is mgh, and we have, then again, I've sort of assumed here my zero of my coordinate system is at the final location of the center of mass of the object. I've defined my potential energy of gravity to be zero at this point as well. That gives me a potential energy function of mgx, where x is the height above this that is the coordinate variable. And so if I start a height above that location, then my initial potential energy is mgh. Okay, so my final energy, I won't have any potential energy, but I'm going to have kinetic energy of translation, which is 1/2 mv squared. And I'll have some kinetic energy of rotation, which is 1/2 I omega squared. So if I conserve energy, I have mgh then is equal to 1/2 mv center mass squared plus 1/2 I omega squared. So we've already decided that I is going to be anything of the generic form, k, which is some constant, times m r squared. And we are also invoking rolling without slipping, so our angular velocity is equal to the tangential velocity of a point on the edge of the rotating object, v sub t, our translational velocity, divided by the radius of the object. And, well, I'm sorry, that's the definition of angular velocity, fine. And the rolling without slipping condition gives us that tangential velocity is equal to the velocity of the center of mass. And so that's all very important to be able to relate our angular velocity to the velocity of the center of mass. And so that now gives us, let's see, right, where I want to do this, I'll move over here. mgh is equal to 1/2 mv center of mass squared plus 1/2 k mr squared times omega squared, which is then velocity of the center of mass squared over the radius squared. Okay, so the r's cancel, and I can pull out then a factor of of 1/2. I'll multiply both sides by 2. The m's cancel, and so this gives me 2gh is equal to, I just have a 1 here, and let's see, hold on, this is the only term left here, and the only terms left here are k and velocity of the center of mass, so I can pull out the velocity of the center of mass squared, and I get 2gh is equal to 1 plus k times the velocity of the center of mass squared. So the velocity of the center of mass then is equal to the square root of 2gh over 1 plus k. Okay, and so this answers our question. The velocity of the center of mass is given by gh, right, divided by 1 plus k. And so the larger the k, the smaller the v. So the larger the k, the smaller the velocity is going to be. So those with a smaller k are going to win the race. Note that this is independent of mass or radius. M, R, I had small r's before. The velocity that it reaches at the bottom, it does not matter on the mass of the object or the radius of the object. A small solid cylinder is going to beat a large hollow cylinder, or a large solid cylinder is going to beat a small hollow cylinder. It doesn't matter on the mass or the radius, only the distribution of matter matters. The how it is distributed about the center of mass, this coefficient k. So in the race, that with lowest k will win, so the solid sphere comes in first with a k of 0.4, then the solid cylinder comes in next with a k of 0.5, and then the spherical shell comes in with a k of 2/3, or say 0.67, and then the cylindrical shell comes in last with a k of 1. All right, but before we go on, I want to look, we have the energy of each of them as simply a function of k. Now I want to look at the distribution of energies for the object as a function of k. Let's look at the ratio of translational to full kinetic energy. So what fraction of the energy goes into translational motion for each of these objects? Okay, well, the translational motion was 1/2 mv center mass squared over the total energy, which was just mgh, the height at which it started. So the masses cancel, and then 1/2 v squared we just found. That's 2gh over 1 plus k divided by gh. The gh's cancel, 2's cancel, and this is 1 over 1 plus k. So there's the fraction of energy that goes into translational motion. That is independent of everything except k. K is the only parameter that it depends upon. Okay, now again, if we go into the fraction into rotational motion, well, that better be k over 1 plus k so that they add up to 1. But we can look at that. It's 1/2 k m then times velocity of the center of mass squared. 1 plus k over GH's that they cancel while the m is already out of there. Well, m, those cancel, and so we get k over 1 plus k. And so the fraction of kinetic energy that's into rotation is k over 1 plus k. So you can see the fraction that goes into kinetic energy is larger for those with a larger k. And so if we have sort of our total energy, and then this is the kinetic energy of translation and the kinetic energy of rotation, how the mass is distributed affects how much energy goes into the rotation and translation, and it's higher for those objects with a larger k, which means a larger amount of matter further from the axis of rotation. Such an object is going to be slower than otherwise by rolling it down the incline.